RNNs read one word at a time. Transformers read everything at once. That single difference built ChatGPT. This is the paper that made it possible. Attention is all you need. Vaswani et al. NeurIPS 2017. Over 140,000 citations. The most influential deep learning paper of the last decade. And it started as a machine translation experiment. By 2017, recurrent neural networks own sequence processing, translation, summarization, speech recognition, all RNN territory. But RNNs had three problems that no amount of engineering could fix. First, sequential bottleneck. An RNN processes word 10 only after finishing words 1 through 9. Every time step waits for the previous one. On modern GPUs built for parallel computation, this is a waste. Second, vanishing gradients. Information from the beginning of a long sentence fades by the time the model reaches the end. LSTMs and GRUs improved this, but never solved it. Third, the compression bottleneck. Encoder-decoder architecture squeezed entire sentences into single fixed-length vectors. Bahadanow attention in 2014 partially fixed this, letting the decoder pick at specific encoder positions, but it still ran on top of an RNN. Still sequential, still slow. Vaswani and colleagues at Google Brain asked a direct question. What if we remove recurrence entirely? The answer was self-attention. Instead of processing tokens one by one, self-attention lets every position look at every other position simultaneously. Here is the mechanism. Each token produces three vectors, a query, a key, and a value. Think of it as a library. The query is a question you are asking. The key is the label on each book. The value is the content inside each book. You compare your question against every label, find the best matches, and read a weighted combination of their contents. Mathematically, the attention score between two positions is the dot product of query and key, divided by the square root of the key dimension to prevent the values from growing too large. Apply softmax to get weight. Multiply by values. Attention of QKV equals softmax of QK transpose over square root DK times V. But one attention head can only focus on one type of relationship at a time, so the transformer runs 8 in parallel multi-head attention. Each head operates on 64-dimensional projections of the 512-dimensional model. One head might track grammar, another tracks meaning, another tracks which pronoun refers to which noun. 8 perspectives combined. And here is a callback to episode 2. Look at the transformer block diagram. Around every attention layer and every feed-forward layer, there is a residual connection, a skip connection. That is ResNet's idea built directly into the transformer. Without those shortcuts, the 6-layer transformer would not train. The results were immediate. On WMT 2014 English to German translation, BLEU scored 28.4, beating the best prior ensemble by over 2 points. On English to French 4.1.0, a new state-of-the-art. The base model trained in 12 hours on 8P100 GPUs. Previous LSTM systems took weeks for weaker results. But translation was just a proof of concept. In 2018, BERT took the transformers encoder stack and trained it bidirectionally, reading left to right and right to left simultaneously. That same year, GPT took the decoder stack and trained it to predict the next word. In 2020, GPT-3 scaled to 175 billion parameters and showed few-shot learning. In 2022, ChatGPT brought the transformer to everyone. But here is where it gets interesting for us. The architecture that conquered language has barely dented medical imaging. Over 90% of FDA-cleared radiology AI devices still run on CNN backbones. Why? 3 reasons. Medical datasets are small, often hundreds to low thousands of labeled images. CNNs come with built-in assumptions that match imaging tasks. Nearby pixels matter more than distant ones. And a lung nodule looks the same whether it sits in the left lung or the right. Transformers have to learn these properties from raw data, which demands orders of magnitude more training examples. Vision transformers match CNN performance on large public benchmarks. But in the clinic, small datasets, high stakes, regulatory requirements, convolutional networks still hold the advantage. The emerging trend is hybrid, CNN feature extractors paired with attention-based reasoning layers, the best of both architectures. Episode 1, Inception, showed efficient design. Episode 2, ResNet, showed depth through shortcuts. Episode 3, The Transformer, showed that attention alone without convolutions, without recurrence is enough. But when the transformer finally came for computer vision directly, that required one more insight. Episode 4, The Vision Transformer. Where do you think transformers will replace CNNs first in clinical radiology, detection, segmentation, or report generation? Drop your prediction below. Follow ScrubCode so you do not miss the next one.